Bismillah ar-Rahman ar-Rahim. In this video, we obtain a lower bound on the ergodic capacity of a MIMO channel. The channel matrix H has NR rows and NT columns corresponding to NT transmit antennas and NR receive antennas. We take NR to be greater than or equal to NT. The elements of H are i.i.d, complex valued circularly symmetric Gaussian random variables with a mean of 0 and a variance of unity. This is the expression for the ergodic capacity. And in this expression, we have S and R. This is the average signal to noise ratio per receive antenna. Here the averaging is over the transmitted symbols and the channels. NT again is the number of transmit antennas. H is our friend here, the channel matrix. It appears as H and H Hermitian. And between them, there is the transmit covariance matrix, which is CXX of size NT by NT. What we will do in this derivation is that we will set CXX equal to identity of size NT by NT. We can optimize over CXX to maximize the achievable rate. But since our task is to lower bound the ergodic capacity, we will just set the transmit covariance matrix to identity. Why are we interested in a lower bound? One objective is to compare the fading MIMO channel and a corresponding AWGN channel. So let's go to the SISO case, in which the transmitter and receiver are both equipped with single antennas. In this case, C is the expectation of log 2, 1 plus SNR, and then the magnitude of H squared. In this case, the magnitude of H squared will be an exponential 1 random variable. For a general distribution, for the channel, the ergodic capacity will be the expectation of log 1 plus SNR, and let's say that G, so G is the magnitude of H squared. Because the logarithm is a concave function, then we can employ Jensen's inequality. The expectation of this logarithm is R bounded by, so this is an application of Jensen's inequality, the logarithm, and then we take the expectation of the argument, which is 1 plus SNR, the expectation of G. What does this inequality mean? It means that for an AWGN non-feeding channel with a gain that is equal to the expected value of G, the capacity is superior to the ergodic capacity. The capacity of the fading channel is less than or equal to the capacity of an equivalent AWGN non-feeding channel. And by equivalence, I mean that the constant gain of the channel is the expectation of G, this channel power gain. The conclusion in the SISO case is that feeding is bad. What we will try to do here is to lower bound the ergodic capacity and to show that if the number of antennas is large enough, then the lower bound on the ergodic capacity can actually exceed the capacity of the corresponding AWGN non-feeding channel. So this SISO conclusion will not hold if the number of antennas employed is large enough. Our first step in lower bounding C is to ignore the optimization over the transmit covariance matrix and just to set it equal to identity. So C is the expectation of log 2, and then we have the determinant of identity of size NR by NR plus the average signal to noise ratio per receive antenna over the number of transmitters, H Hermitian. We can employ Sylvester's determinant identity, which implies that this determinant here can be rewritten as the determinant of an NT by NT matrix. Recall that we take NR to be greater than or equal to NT plus SNR over NT, and then we have H Hermitian H. Let's recall what is Sylvester's determinant identity. If we have a matrix A and a matrix B, this is M by N, this is N by M, then the determinant of I of size M by M plus AB is equal to the determinant of identity of size N by N plus BA. Let's do a quick proof. Let's compute the determinant of the matrix here with 4 blocks. Here we have identity of size M by M, here we have identity of size N by N, here we have minus A, and here we have the matrix B. Now this determinant is the determinant of, I can take this matrix and I can multiply it from the left by another matrix, and this other matrix also has 4 blocks. Those are identity of size M by M, then A, then identity of size N by N, and here we have 0 of size N by M. Why is this determinant equal to the determinant of the product? The reason is that we have here 2 square matrices, each one is of size M plus N times M plus N. The determinant of the product is the product of determinants. And what is the determinant of this matrix here? It is upper triangular with 1s on the main diagonal, and so the determinant is equal to unity. The determinant of this matrix is equal to the determinant of this product. And it is also equal to the determinant of this matrix of interest. Now, what we will do is that we will multiply from the right by the matrix I, M by M, A, 0, N by M, and then I, N by N. Same thing, that this determinant is exactly equal to the determinant because this matrix has a determinant of unity. We are trying to compute the determinant in 2 different ways. Let's see what we will get from here and what we will get from there. Let's actually do the matrix multiplication. Here we have identity by identity, that's identity, and then we have AB. Then we have identity times minus A plus A times identity, that's the O0 matrix. Then we have 0 times identity plus identity times B, that's B here. And then finally we have 0 times minus A plus identity, so we get identity of size N by N. This is a block lower triangular matrix, and the determinant is the determinant of this block times the determinant of this block. The determinant of identity is 1, and so this is the determinant of identity. Specifically, this identity is of size m by m plus the m by m matrix AB, because A is of size m by n and B is of size n by m. Now let's complete the determinant in another way. Let's do the product. What is the product here? We have identity by identity minus A times 0. That's I of size m by m. Then we have identity by A minus A by identity. That's the O0 matrix. Then we have B plus identity times 0. That's B matrix. And finally, we have BA plus identity. And again, by the same rule that we applied here, the determinant of this matrix is the determinant of this identity, which is unity, and then the determinant of identity, now of size n by n plus BA. So these two determinants are exactly equal. In our case, we are able to write down the capacity using the identity of size nt by nt. Here we have nr greater than or equal to nt. The determinant of the matrix is the product of its eigenvalues. So this is the expectation of the logarithm to the base 2 of a product. And this product is k from 1 to nt. And then we have the eigenvalues of this matrix. Let's focus on the eigenvalues of H Hermitian H. Suppose that the kth eigenvalue of H Hermitian H is lambda k. Let's put here between brackets H Hermitian H to indicate that those eigenvalues are those of this specific matrix. Now, if we multiply the matrix by a scalar and then we add identity, then the eigenvalues of this matrix here are the lambdas times S and R divided by nt, and then we add 1. The logarithm of the product is the sum of logarithms. So this is the expectation of the summation k from 1 to nt, and then we have log to the base 2, 1 plus S and R over nt, and then we have lambda k, H Hermitian H. Consider lambda. Lambda is a randomly picked eigenvalue of H Hermitian H. The eigenvalues of this random matrix here, if they are unordered, then they are identically distributed, which means that this expectation of the sum can be written as nt, the number of terms in the sum, and the number of the eigenvalues of the matrix H Hermitian H. And then we take the expectation of one term, log 2, 1 plus S and R over nt times lambda. Again, lambda is a randomly picked eigenvalue. It's an unordered eigenvalue of matrix H Hermitian H. The expectation here is with respect to lambda. This is our random variable. Now, let's lower bound by inserting an indicator function in the expectation. I will insert the indicator function that lambda is strictly greater than eta. So what is eta? Eta is strictly positive, and let's take it to be strictly less than the expectation of lambda. This is a lower bound because here we have ones, but this one is replaced by the indicator. The indicator is 1 if lambda is greater than eta. The indicator is 0 if lambda is less than or equal to eta. If we have indicator lambda greater than eta times log to the base 2 1 plus S and R over nt lambda, then this is lower bounded by the indicator. And then here we can replace this lambda by eta, log 2 1 plus S and R over nt, and then we put this constant eta. Why is this true? If lambda is less than or equal to eta, this indicator is equal to 0. That indicator is less than or equal to 0. We have the inequality that 0 is greater than or equal to 0. That's fine. It is a correct mathematical statement. Now, if lambda is greater than eta, then both indicators are equal to 1. And if lambda is greater than eta, because the logarithmic function is strictly increasing, then the log of 1 plus S and R over nt lambda is greater than log 1 plus S and R over nt eta. This inequality here is verified. The advantage of doing this step is that this term now is a constant, and we can take it outside the expectation. So this is equal to nt log to the base 2 1 plus S and R over nt eta. Now we have the expectation of the indicator. This is like a Bernoulli random variable. It can take two values, 0 or 1. So the expectation of this Bernoulli random variable will be the probability that this event is true, specifically the probability that lambda is greater than eta. To further lower bound the ergodic capacity, we need a lower bound on this probability. We need a lower bound on the probability that lambda is greater than this positive quantity eta. We will employ the Paley-Zygmund inequality. And it gives us a lower bound that will depend on the first and second moments of this random variable. Let's remind ourselves of the Paley-Zygmund inequality. Suppose that you have a positive random variable z. Let's take the expectation of z, the first moment of z. This is the expectation of z, and then I can insert here an indicator that z is greater than eta, plus z times the indicator that z is less than or equal to eta. By the linearity of expectation, this is the expectation of z indicator z greater than eta, plus expectation of z indicator that z is less than or equal to eta. Let's focus on this term first. This is upper bounded by eta times the indicator that z is less than or equal to eta. If the indicator is 0 because z is greater than eta, then we have 0 less than or equal to 0, which is okay. If the indicator is 1 because z is less than or equal to eta, then z is less than or equal to eta, and then we can apply the expectation. This is equal to eta times the expectation of the indicator, which is the probability that z is less than or equal to eta. But any probability is less than or equal to 1, so this is less than or equal to eta. This term here can be upper bounded by eta. What about this? For this guy, we can apply the Cauchy-Schwarz inequality. this expectation of the product of two random variables. Z is one random variable and the indicator is another random variable. This is less than or equal to the square root of the expectation of Z squared times the square root of the expectation of the indicator squared. The indicator is 0, 1. And so the square of the indicator is itself. Here we have under the square root, we have the second moment of this positive random variable Z. And here we have the expectation of the indicator, which is the probability that Z is strictly greater than eta. The right-hand side was split into two terms. One term is upper bounded by eta. The other term is upper bounded by the square root of the second moment of Z times the square root of the tail probability that Z exceeds eta. Now we can move eta to the other side. So the expectation of Z minus eta is less than or equal to the square root of the second moment, the square root of the probability of interest. Suppose that eta is less than the expected value of Z. In this case, this guy is positive and this is positive. We can square both sides and we can divide by this guy here to get the following lower bound, the probability of Z superior to eta. This is lower bounded by the expectation of Z minus eta all squared divided by the second moment of Z. This is the Paley-Zygmund inequality. In our case, we get the same result. It is just that we need to obtain the moments of the random variable lambda. The lower bound is the expected value of lambda minus eta all squared divided by the second moment of lambda. Lambda is an eigenvalue of H Hermitian H. How can we obtain the first and second moments of lambda? Here is the trick. Now lambda is a randomly chosen eigenvalue of H Hermitian H. I can write it as 1 over nt and then a summation of the eigenvalues, the unordered eigenvalues, like this. What is the benefit of writing down the expectation in this way? Here we are exploiting the fact that the eigenvalues are identically distributed, so they have the same moments. The benefit of rewriting this expectation as an expectation that involves the sum of the eigenvalues is that we can replace the sum of the eigenvalues by the trace of the matrix. This expectation here is 1 over nt, and then the expectation of the trace of H Hermitian H. The claim is that handling or managing the trace is easier than just working with an eigenvalue. What is the expectation of the trace of H Hermitian H? Let HK be the kth column of H. This matrix is H1 Hermitian, H2 Hermitian, all the way to HNT Hermitian. This is H Hermitian times H itself, which has those columns H1, H2 to HNT. What are the main diagonal elements of H Hermitian H? Those will be H1 Hermitian H1 and H2 Hermitian H2 and so forth. So the trace, which is the sum of the eigenvalues, is also the sum of the main diagonal elements. The expectation of lambda is 1 over nt, and then we have the expectation of summation k from 1 to nt. And the kth main diagonal element is HK Hermitian, HK, like this. This is the L2 norm squared of the column vector HK. 1 over nt, expectation, summation k from 1 to nt, and then summation j. Note that HK is a column in matrix H, so it lives in the complex NR dimensional space. So we have the L2 norm squared of column vector HK is summation j from 1 to NR. That's the number of rows in H, and this is the number of the receive antennas. This thing here will be HVK, and then we take the magnitude squared. This is the L2 norm squared of this column vector here. Recall that each one of those guys is exponential one random variable with a mean of 1. When we apply the expectation, all those expectations will be equal to 1, and we are left with the number of terms in this double sum, which is NR and T. Don't forget this guy here, and we end up with NR. So the first moment of the eigenvalue is equal to the number of receive antennas, or the number of rows of the random channel matrix H. Now we have a bit more difficult task, which is to obtain the second moment. What is lambda squared? But we will use the same trick. This is 1 over nt, and then we have the expectation of a sum k from 1 to nt, lambda of H Hermitian H squared, and this is lambda k. In other words, suppose that we have matrix H Hermitian H, and its eigenvalues are lambda 1, lambda 2, all the way to lambda nt. What are the eigenvalues of H Hermitian H squared? Those will be lambda 1 squared all the way to lambda nt squared. If those eigenvalues are unordered, they are identically distributed, and the expectation of one of them is simply the expectation of the sum divided by their number, which is nt. Now we can write this summation as the trace of H Hermitian H squared. That's H Hermitian H Hermitian H. This is 1 over nt, and then we have the expectation. And then what is element kk here in this matrix? This matrix is of size nt by nt. So a summation k from 1 to nt. What are the main diagonal elements? Now, if we take the kth row from here, so this will be HK Hermitian, and then we will have this matrix of size NR by NR, that's H Hermitian, and then from here we need the kth column, that's HK. This is element KK on the main diagonal of H Hermitian H squared. The sum of those guys will give us the required trace. We have H Hermitian here. We can write this as H1, H2 to HNT, that's H, and then here is the Hermitian, H1 Hermitian all the way to HNT Hermitian. And we can write down H Hermitian as a sum of the outer products of the columns of matrix H. In other words, this is 1 over nt, then we have the expectation, then we have summation k from 1 to nt. Then we have hk Hermitian. H Hermitian can be written as summation j from 1 to nt, and then we have the jth column multiplied by its Hermitian, and then we have hk. This is 1 over nt, and then we have expectation. We have a double sum, k from 1 to nt, j from 1 to nt, and then we have hk Hermitian hj, and then hj Hermitian hk. So hk Hermitian hj, that's a complex scalar, and hj Hermitian hk, that's the complex conjugate of this scalar. This is simply the magnitude squared of hk Hermitian hj. This is the magnitude squared of the inner product between column vector hk and column vector hj. Let's write down this inner product. It is summation small r from 1 to nr, because each one of those column vectors has nr elements. So summation r from 1 to nr, and then we have h, k, that's the kth column of matrix H. Now we are talking about its rth element, and we have a Hermitian here, so we need to put a conjugate, and then we have h, this is column j, then element r. This is the inner product, but we need its magnitude squared. We need to take the magnitude squared of this sum. So we end up with two more sums. So we have summation k from 1 to nt, we have summation j from 1 to nt, we have summation r from 1 to nr, and then we have summation s from 1 to nr. Let's copy and paste. This is hrk conjugate, hrj, and then we have h, let's replace r by s, so s and k, and then we conjugate the conjugate. And finally, we have h, we replace this r by s, j, and then we conjugate. So this is what we have. By the linearity of expectation, we can just take the four sums, apply to the expectation of hrk conjugate, hrj, hsk, hsj conjugate. Now we have a rule for the product of four zero mean circular symmetric Gaussian random variables. This rule that I'm about to write can be derived using the joint characteristic function of those random variables. The rule tells us that this expectation of this product of four terms can be written as an expectation of, then we take A and one of the conjugated random variables, let's say we take AC conjugate, times the expectation of the other two guys, that's B and then D conjugate. Are we done? Not yet. Plus the expectation. Then we take A again with the other conjugated random variable, which is D, and we multiply this expectation with the expectation of B times C conjugate. Rather than having to deal with the expectation of the product of four random variables, now we do them in pairs. Let's apply this rule to our case here. What is this expectation? So it is expectation of, if I take this guy, hrk conjugate, then I take one of those random variables without the conjugate. Let's say I will take hrj. Then there will be the expectation of the two other guys, hsk, hsj conjugate, plus expectation of, now we take this, hrk conjugate. The first time we employed this, now we use that, hsk, and then we take the expectation of the remaining two random variables. In our case, those are hsj conjugate, and finally hrj. Remember, our H matrix, its dwellers are the i.i.d, c, and 0, 1 random variables, which means that whenever we take the expectation, we need the indices to be the same so that we get a non-zero result. If we do this expectation here, we have r and r, that's fine, but then we have k and we have j. This expectation will give us 1 if and only if k is equal to j. Let's write this as delta kj. This is like the discrete time delta. This is 1 if k is equal to j, 0 otherwise. If we apply this idea here, we get delta kj. And if we apply this idea here, we get delta rs. And if we apply this idea here, we get delta rs. When we apply these four sums to delta kj, it means that index k must be equal to index j. But r and s can be anything. When we apply the four sums to the product of these two expectations, we will get nt times nr squared. Because r goes from 1 to nr, s goes from 1 to nr, and k and j go from 1 to nt, but they must be the same so that we don't get a zero answer. We get unity. Therefore, we get nt. This corresponds to k equal to j equal to 1, k equal to j equal to 2, all the way to k equal to j equal to nt. When we consider these two guys, now r must be equal to s, and k and j are free. So this will give us nt squared. Nt from summing over k, another nt for summing over j, but then we get nr. When r is equal to s is equal to 1, r is equal to s is equal to 2, and so forth. This is the result of applying these sums. We finally divide by this nt. So we get nr squared plus nt nr. This means that the second moment of lambda squared, this is nr, and then we have nr plus nt. Now we have our first and second moments of the random variable lambda. Let's quickly revise our steps. We started with the formula of the ergodic capacity. We started the series lower bounding from here, inserting inside the expectation an indicator that lambda is greater than eta, a positive parameter that is chosen to be less than the first moment of lambda so that we can employ the Paley-Zygmund inequality. We lower bounded this indicator times the logarithm by the indicator times the logarithm with lambda replaced by eta. This is no longer random and we can take it outside the expectation. The expectation applied to the indicator gave us this probability that the randomly selected eigenvalue is greater than eta. It is here where we used the Paley-Zygmund inequality, lower bounding the probability by a term that needs both the first and second moments of lambda. We turned our focus to obtaining these moments. And the idea was to exploit the fact that the unordered eigenvalues are identically distributed. So the expectation of lambda can be written as the expectation of the sum of the lambdas divided by their number, which is nt. And the expectation of lambda squared can be written as the expectation of the sum of the lambda squares divided by their number, which is nt. The trick was to write down things in terms of the trace of h Hermitian h and the trace of h Hermitian h squared. These are manageable. And also we used this nice result about the expectation of a product of 4 zero mean Cn random variables. We obtain the moments, and now let's write down the lower bound. Nt log to the base 2, 1 plus SNR over Nt, and then we have eta. Then we have the expectation of lambda, that's Nr minus eta squared divided by the second moment. Here is the second moment, Nr plus Nt. That's our lower bound. For simplicity, suppose that Nr is equal to Nt is equal to N. So we are deploying the same number of transmitters and receivers. And suppose that eta, this parameter, which must be less than Nr, take it to be N over 2. The lower bound is from here, we have N. Inside the logarithm, we have, this is N, and eta is N over 2. This is SNR over 2. N minus N over 2, that's N over 2 squared, that's N squared over 4. And in the denominator, we have N squared times 2. This is equal to N over 8 log to the base 2, 1 plus SNR divided by 2. Suppose now that all our channels are non-fading AWGN channels with a constant gain of unity. What will be the capacity? The non-fading case will have a capacity log to the base 2, the determinant of I n by n, and then we have SNR divided by n. Now the channel matrix is an all-one matrix of size n by n. The channel matrix can be written as n columns, all of them are equal to D, and D is the all-one vector in n-dimensional space. H Hermitian will be like this. This is log to the base 2 determinant, and then we have identity of size n by n plus SNR over n, and then we have D times D transpose plus D times D transpose. We have n of those guys. We can write down this term as SNR times D transpose. Note that this is n by 1 and this is 1 by n. We can employ Sylvester's determinant identity and write down this determinant as that of 1 plus the SNR and then D transpose D. This is a scalar, and the determinant of this 1 by 1 matrix is just itself. This is log to the base 2, 1 plus this inner product of the all one vector by itself, that's n SNR. We have a fading case, then we have the non-fading case. Here we have a lower bound, that's n over 8 log to the base 2, 1 plus SNR divided by 2. In this case, we have log to the base 2, 1 plus n SNR. Observe that the number of antennas here is in the pre-log factor. This lower bound on the ergodic capacity increases linearly with n. In the non-fading case, n is inside the logarithm. This also increases with n, but with a logarithmic trend. This means that if n is large enough, given some SNR, we can make this greater than that. With a large enough number of antennas, random i.i.d fading in MIMO systems may improve capacity, contrary to the SISO case.